This is Lab 4 Circuits by Melanie Weaver. To begin, capacitors store charge in a similar way to how buckets store water, and we will be using capacitors in the simulations for this lab. The loop rule states that the sum of all potential differences around one path of a circuit is zero. Ohm's law says that voltage is current times resistance, and the purpose of this lab was to predict circuit behavior, measure potential difference and current with multimeters, which we actually used ammeters and voltmeters, and to examine the behavior of ohmic resistors and capacitors. The RC value that I got was 5.988 seconds. So for the experiment, the first thing that we had to do was to create a series circuit with two 1.5 volt batteries, one 47 ohm resistor and 100 ohm resistor, and you had to put two ammeters at different positions in the circuit, and I predicted using Ohm's law that there would be 0.02 amps at both, and that's what happened. When you turn one of the ammeters backwards, it read negative 0.02 amps, which is because the current is now flowing in the opposite direction through the ammeter. And the ammeter read 0 amps and the voltmeter read 3 volts when an ammeter was replaced with a voltmeter, because when you put the voltmeter in series with the circuit instead of in parallel, the current can no longer flow through it because of the great amount of resistance that it has. So you still read the potential difference, but since the current can't go through the voltmeter, it is an open circuit, and the other ammeter reads 0 because there's no current there. So again, in this same series circuit, we had to read the potential difference at different places. So between A and B, it was 3 volts, B to C was 0, C to D was negative 0.959 volts, D to E was 0, E to F was negative 2.041 volts, and the rest was all 0. And they should sum to 0 because of the loop rule, and that's what they do. So this little chart shows the same thing with the potential difference rises and falls. So in the beginning, when you go through each battery, it rises about 1.5 volts, and then it decreases when you go through the 47 ohm, and it decreases stronger when it goes through the 100 ohm. And at the places where there is 0 potential drop, it shows that there is 0 resistance in the simulation for the wires and the ammeter. So for more results, when you put the ammeter in parallel with the resistor, it increases the current because the current can now flow through the ammeter with relatively 0 resistance instead of having to go through the resistor itself. The resistance of the 47 ohm resistor was 47.95 ohms, the 100 was 102.05 ohms, and there is 0 resistance in both the wire and the ammeter. So next we had to create an RC circuit, which we first had to charge the capacitor. In the beginning, the bulb started out bright and dimmed while the current decreased, and it took 7.8 seconds to fully charge the capacitor with a 10 ohm resistor, and it took 13.1 seconds for the 20 ohm resistor, and the image of the circuit is after the capacitor is fully charged. And then discharging the capacitor, just the same as charging, the bulb started out bright and dimmed while the current decreased, and it took 8.4 seconds to discharge the capacitor with a 10 ohm resistor and 14.3 for the 20 ohm, which these values are relatively good because it should take the exact same amount of time to charge and discharge the capacitor with the same amount of resistance in the light bulb, and it was about the same, only a little bit different. So this graph again shows the time and the drops in potential difference. So we had to graph it with the natural log of the change in potential difference over the original potential difference, and using that we could find the slope, which the slope is negative 1 over RC. So using the line of best fit, I got that my slope was negative 0.167. So then my RC value ended up being 5.988 ohm farads, which is the same as seconds. And with the values of the 30 ohm resistor and the 0.2 farad capacitor, you expect the RC to be 6 by just multiplying them together, and that is almost exactly to what I calculated, or that's what I calculated. It's almost exact to what my design showed. So for the questions, if you're doing this lab in real life and used an actual ammeter, the ammeter would have a slight resistance, which would alter the result, and you would also have a slight potential drop across the ammeters. So basically everything would be slightly off. And if you're doing this lab in real life with a real battery and a real capacitor with no resistor in the circuit, the battery might not be exact with the amount of voltage that you want, and there would be more resistance going through the wires because real wires have slight resistance, same with real ammeters. However, in the simulation, they are perfect and they have zero. And again, it would charge quicker without a resistor than it would with a resistor. And it would still be quicker than with a resistor in real life. However, it would be slower, as I said, because there would actually be a slight resistance in the wires and the ammeter. So to conclude, we simulated electrical circuits. We observed how capacitors, resistors, and light bulbs act in a circuit. We showed the differences between parallel and series connections. We used ammeters and voltmeters to prove the loop rule, and the computed value of RC was 5.988 seconds. Thank you.